Welcome back. In this video we're going to continue our march towards general relativity by seeing how to make the jump from metrics in space, like the plane or the sphere, into metrics in space-time, which is what we're really interested in. And to do that we're going to talk about special relativity. So if you haven't studied special relativity before, then this may come as a surprise, but if you have, then you already know. But in special relativity, different observers disagree about times and lengths. So what do I mean by that? I mean that if I get on a rocket ship and I start zooming away from you at a very high velocity, near the speed of light, for example, and in my rocket ship I have a ruler and a clock, and you're looking at me flying away in my rocket ship with a powerful telescope, to you it will look like my ruler is shorter. My ruler has gotten shorter than it was when I was at rest, and it will look like my clock is ticking too slowly. These are called length contraction and time dilation. To me, of course, it doesn't look like this. I'm on my rocket ship and I look and my ruler is 1 foot long. It seems perfectly normal and my clock is going at the normal speed. But if I look back at you on Earth, then I will think your ruler is too short and your clock is moving too slowly. So this is strange, and it leads to a lot of interesting physics, which I'm not getting into here. But there is one thing that the observers agree upon. So what they agree upon is a certain number, which I will suggestively write as ds squared. But that's calculated like this. So you take the speed of light squared, dt squared, and then take the spatial separation between two events and add them together. So this means, for example, if I'm on my rocket ship and a firecracker goes off at one end of the rocket ship and at a later time another firecracker goes off at the other end, and I calculate this number, which is I use my clock to see how much time passes between the two firecrackers, and I measure the length between the front and end of the ship, the length between where the firecrackers went off, and I take minus c squared times the change in time squared plus the change in the length squared and add that all together to get some number. And you, using your telescope, calculate the same number using your clocks on Earth, you'll get the same number. So that's interesting. That's the main crux of special relativity, and this is what you use to kind of to show how special relativity generates interesting physics and predictions about energy conservation and momentum conservation, for example, when you define suitably generalized ideas of momentum and energy. But anyway, so because everyone agrees upon this, we'll use this as the definition of the distance between events in space-time. So we will use this as the definition of distance. So, for example, when the two firecrackers went off, those represent two different points in space-time, because they each have a space coordinate and a time coordinate, and the distance between those points will be this guy. So let's try to write that like we've been doing before. So in our metric language, so that's if we make this vector dt, dx, dy, dz, and put in our matrix, so we'll need a minus c squared, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and put a column vector in dt, dx, dy, dz. Okay, so now we have a space-time metric. Let me switch colors. So the space-time metric is typically written as eta mu nu. So this is eta mu nu. So this is a matrix or a tensor. It has two indices. And what's different from the metrics we've seen before is this has a minus sign on the time component. And that's the main defining feature of time, is that it has a minus sign in the metric. So now we can have distances between points being negative, which is interesting. But our ultimate goal is to understand a curved space-time. And as you can see, this metric doesn't depend on t, x, y, or z. So when we take derivatives of the metric to get those Christoffel symbols, it'll still be 0. And I want to motivate for you why we need a more complicated object than the Christoffel symbols to detect curvature in space-time. So to do that, what if we wrote the same equation for this distance between space-time points, but we wrote it in spherical coordinates? What about that? So what would happen? Well, in this case, we would have, as we saw before, ds squared, well, minus c squared dt squared stays the same. And then we'll have a dr squared, because now we're in r theta phi, but we saw before that we got a different setup for the metric for the theta and phi components, and that was we had an r squared d theta squared plus r squared sine squared theta d phi squared. That's what we saw in a previous video. So this has a metric eta mu nu spherical. So I'm just going to skip right to this. So we still have a minus c squared here, 0, 0, 0, 0, 1, 0, 0, 0, 0, r squared, 0, 0, 0, 0, r squared sine squared theta. So all we've done is take the metric for a flat space-time, this eta mu nu, from special relativity. Special relativity we'll say is flat because it doesn't have any forces acting, and everything moves in a straight line in special relativity. So we took that metric and then wrote it just using spherical coordinates. But now this metric does depend on where you are. For example, if you take a derivative with respect to r, you'll get something non-zero because of these r squared terms. But we still want this metric to represent a flat space-time because in special relativity everything moves in a straight line. So we don't want that to be space-time curvature. So how can we define curvature? How can we define curvature so that it captures this more nuanced notion of a curved space-time so that this guy is still flat, which means not curved? How to define curvature? So to do that, we're going to need a more complicated object than the Christoffel symbols, and I'll show this in the next video. We'll start talking about the Riemann curvature tensor, and once we understand that, we can start writing down Einstein's equations. Thanks for watching.